Okay, uh, okay, so the first thing is a week from Wednesday is exam 2. I still need to think a little bit about what topics are going to be on it. Definitely everything up through free body diagrams. That's probably all it's going to be, but I need to think about it. And remember that in this class, all the tests and all the quizzes too are cumulative. So you're going to want to go back and refresh your memory on some of the older problems too to get ready for this. Okay? But that's still, what, 9 days away? I didn't assign any homework over the break, but does anyone have any questions, anything you thought of that you'd like me to answer? Okay. Well, so where we are right now is we're talking about free body diagrams. Newton's second law says that F net, if you add up all the forces on the body, that's equal to the mass of the body times its acceleration. And so since free body diagrams show you all the forces acting on a body, free body diagrams give you everything you need for the left side of Newton's second law. Okay, so we'll draw a free body diagram. It has all the forces in it. Then all you have to do is put those in vector component form, and that gives you the left side of the equation. Then all you have left to worry about is basically the acceleration, you know. And I gave you a list of force types. So these are all of the forces that we're going to deal with in this class. First is the weight force. That's the force applied by gravity. And second is contact forces. And we can break down contact forces into 3 different ones. The first one is pushing forces. And to know the direction of the pushing force, it's always perpendicular to the surface. Toward the chosen body. The next one is a pulling force. And even when something is being pulled without using cables, you can imagine it being done by a cable. And the rule for the direction of this is parallel to the cable, or parallel to how the cable would be positioned if you replaced the contact with a cable. parallel to the cable, away from the chosen body. The weight force is always just down. That one's easy. And then the last one we still have to talk about is friction. And so we'll get into that today. But before we do, I just want to do an example or two, because it's been a while, showing you how to do what we've done so far. Okay, so let's say that we have a ramp and two carts are on the ramp connected by cables. Let's say this one is 5 kilograms and this one is 4 kilograms. And let's say that there's a force. We don't know what's applying this force. We just know what the force vector itself is. But let's say there's a 50 Newton force pulling this system of carts up the ramp. And we want to draw free body diagrams for each one of these. So I guess I'll start with the 5 kilogram. So I'm going to draw it at the angle that it's at. The weight force goes straight down, and that's equal to 5 kilograms times 9.81 meters per second squared. So 5 times 9.81 is 49.05. And now that we've dealt with the weight force, all we have to do is go around the boundary of this and look for places where other objects contact the boundary. I guess first I'll do the one that's given. We know that there's a force going this way of 50 newtons. Now from that point, if I keep going counterclockwise around the boundary, eventually I get to the wheels. It's a pushing force that's being applied to these wheels. Like if you replace the contact with the ground with some kind of cable, the cable would just collapse. It can't keep this cart from sinking into the surface. And so this has to be a pushing force. And so the rules say perpendicular to the surface, away from the boundary, toward the chosen body. And I'll call this N for normal force. I guess maybe I'll call it N5 since I can see there's going to be a normal force for the 4 also, and I don't want to mix those up. And since we're still doing particle stuff, it doesn't really matter where you apply these forces. So we don't have to worry yet about whether how this force is divided up over the different wheels, because we're treating everything like it exists at a single point anyways, okay? And then keep going counterclockwise around and you get to the cable connecting these two bodies. Well, if it's a cable, it has to be a pulling force. So that force is parallel to the cable, away from the body. And we don't know what the magnitude of that is. I'm going to label it T for tension. Any questions about that one? And now free body diagram of the 4 kilogram. There's a downward weight force of 4 times 9.81, so that's 39.24. I'll start on the left side. On the left side, there's a cable, the cable that connects those two bodies. So that's a pulling force, so it has to be this way, away from the body. And since that force is applied by the same cable as this one, we're going to use the same variable. Keep going around and you get to the contact with the ground. That's a pushing force. And I'll call that N4. The different subscripts on these just mean those are different variables. So this one has the name N5, this one has the name N4. And keep going around. Is there any other place where the surroundings make contact with this body? Nope, that's it. And so what we have now is a drawing of every single force that we would put into Newton's second law on the left side. Okay. Okay, so let's talk about the last one, friction. So friction is a force that resists, or a force resisting sliding along a surface. There are two types of friction forces. The first one is called static friction. Static means still, not moving. So static friction is a friction force that resists sliding in an object that's currently at rest. And the second type is kinetic friction. And that is friction that tries to slow down sliding that's already occurring. There's no particular reason I would choose one of these over the other, but just in the interest of time in this class, we're not going to do calculations with static friction. We're only going to do calculations with kinetic friction. Okay. And one thing that you want to remember, so notice, friction always occurs along with a pushing normal force that pushes the objects together. Okay, so for kinetic friction, what do we know about it? The direction is always exactly opposite the direction of the velocity of the object. So you can think of that as the velocity vector. It's opposite the velocity vector. And the magnitude of the friction is always going to be, that's the Greek letter mu. So it's always going to be this Greek letter mu times n. And I'll tell you what each of these things are. Mu is a positive number representing the two materials in contact with each other. And so if you have a wood block sliding along concrete, smooth concrete, you have some amount of friction. If instead you have an iron object moving along a smooth steel surface, you have a different amount of friction. That's determined by this coefficient of friction. So that's what this is called, coefficient of friction. And N is the normal force pushing the surfaces together. Or pushing the materials together. So as far as having a feel for what various coefficients of friction are, if you have like an ice cube sliding along ice right at the freezing point, well, you can imagine that's not going to have a lot of friction. And the coefficient in that case is 0.02 about. Rubber on concrete is kind of like the other extreme. You know, there's a lot of grip between those two things. And you get a value somewhere around 1. It can be a little more, a little less, depending on the type of rubber and stuff like that. So mostly the values are going to be between 0 and 1, although there's no rule saying that it has to be less than 1. Okay, so let me show you an example with friction. Let's say this has a mass of 10 kilograms. And let's say we're applying a 30 Newton force to the object in that direction. And let's say the coefficient of friction between the block and the surface is 0.3. And we want to draw a free body diagram of the block. Well, we know there's a 30 Newton force applied here. There's a weight force straight down of 10 times 9.81, so that's 98.1 newtons. Okay, and now, and I actually forgot something really important here. What I drew here is not enough to know which direction this is sliding at this instant. Like, it could be sliding, it could have been going 100 miles an hour when this, imagine that this thing was moving 100 miles an hour to the left in that picture when that force is applied. Well, it wouldn't stop instantly. It would take a while to stop. And so it could still be moving to the left even though the force is pushing to the right. So I have to tell you in problems which way it's sliding. So let's say that it's sliding in this direction. Okay. So you could think of that as the direction of the velocity or the direction that it's moving at that instant. Okay, well, the friction has to occur with a normal force. Those always occur together. The normal force is the force applied to the block by the ground. That's a pushing force, so it's going to be toward the body, and I'll call that N. And then the friction force is going to be opposite the direction of motion. And it's going to be equal to the coefficient times the normal, which in this case means 0.3 times the normal. Okay, so that's a complete free body diagram for that object. Anybody have any questions about that? Okay, let's say we have a block on this surface. Let's say this has a mass of 2 kilograms and it's connected to a hanging mass by a cable that goes over this pulley. And let's say at this instant, the sliding object is moving to the left. That means the hanging object is moving down. And let's say the coefficient of friction is equal to 0.1. And we want to draw a free body diagram of each of these two masses. Okay, so first I'll do the 1 kilogram. There's a weight force of 1 times 9.81, so that's 9.81 newtons. Then there's only one place where the surroundings make contact with the boundary. Where's that? Yep, at the top, the cable does. That's a pulling force. So the force is parallel to the cable, away from the body, and I'll call that T. So notice there was nothing in this free body diagram that the direction mattered for at all. But with the friction, there will be. Okay, so on the 2 kilogram, there's a weight force of 2 times 9.81, so 19.62. Then going around the boundary, there's a cable force here that's parallel to the cable, away from the body. And since it's the same cable as this one, we give it the same name. And then for the friction force, we know there's a pushing normal force. So that's this way. I'll call that N. And then the friction is the opposite direction of what the object's moving. The object's moving to the left, so this friction force has to be to the right. And it's equal to the coefficient, 0.1, times that normal force. Anybody have any questions about that? And just as a reminder, I write newtons a lot on problems like these, like this 30 Newton force here, and I write normal forces a lot. And if you get those two confused, it's going to mess up your answers. I always, when I'm using N as a variable representing a normal force, I always put the fancy shoes and hat on it. Okay, that's how you can tell when I write. When I write newtons, I always just have a plain capital N. Okay? But be sure that whatever you do to keep them straight, colored pencils or whatever, just make sure you keep those two things straight. So what this is saying in the friction case is it's saying you take that coefficient and then you multiply it to whatever that normal force is. So if it turns out this normal force is 56 newtons, then the friction force would be 0.1 times 56. And so that would be 5.6 newtons going to the right. Okay, let's, I'll give you a couple of examples and give you a little time to work through them. So first, let's say we have, let's make these rolling. So let's say we have these two carts that are in contact. And let's say that this one is 5 kilograms, this one is 3 kilograms, and let's say that there's a pushing force over here of 20 newtons, and a pushing force the opposite direction of 50 newtons. And anytime I draw wheels, you can think of that as a shorthand way of me telling you that there's no friction there. So these can move freely back and forth, okay? Also, you know, I'm not giving you a coefficient of friction, and I'm not telling you the direction of the velocity at this instant. Those are all hints that say, okay, there's no friction to deal with in this problem. So take a couple minutes and draw a free body diagram of each of these masses. So here's the outline. We know there's a 20 Newton force. We don't know what's applying that. And then the weight force goes straight down. 3 times 9.81 is 29.43. There's a pushing force on the wheels from the ground, and that's toward the chosen body. I'll give that the name N3. And then the only other place where the surroundings contact the boundary is where the two carts are in contact with each other. That's a pushing force. And so it's perpendicular to the surface toward the chosen body. And I'll give it the name R, but that's just a variable name. You could give it any variable name. Any questions about that one? And now the 5. Well, notice the 20 doesn't act on the 5. It doesn't act on the boundary of the 5. The 50 does. And so the only one of those two that appears here is this. There's a weight force acting down of 5 times 9.81, 49.05. There's a pushing force from the ground. I'll call that N5. And then the last thing is a pushing force applied by the 3. That's toward the chosen body. And since that's a contact between these two, you give this the same variable name as you gave it over here. So that's R. These two have to be the same value, even though the directions are opposite. Okay. Anybody have any questions about those? Anything that you did differently and you're not sure why? Okay. Well, let me take these now and write out what F net would be based on all of these, okay? So F net for the 3 kilogram, that's just the sum of all these forces. And I guess just to be clear, I'm using this coordinate system to come up with these vector components. Okay, so the 20 Newton force, is that in the X or the Y or the negative X or the negative Y? Positive X, and so I'll write that as 20, 0. R, is that, which one of those is R? That's in the negative X direction. So I'll write that as negative R, 0. (29.43) is in the negative Y. N3 is in the positive Y. And so that's the entire left side of Newton's second law. Then for the 5 kilogram, that R is in the positive X direction. The 50 is in the negative X direction. The weight is in the negative Y direction. The normal is in the positive Y direction. And that's everything on the left side of Newton's second law. Okay. Let's do one more example like this, and then we'll go on to how to use this in Newton's second law. So let's say we have an incline. Let's say both of these are inclines, but they're not at the same angle. And there's a pulley in the middle. And on this side, there's a box with friction. And on this side, there's a cart. Let's say that this one has a mass of 5 kilograms. This one has a mass of 1 kilogram. And at the instant shown, they're moving this direction. And the coefficient of friction for the 5 kilogram is 0.2. And we want to draw a free body diagram of each mass. Okay, so take a couple minutes and see if you can think through this.